Alright, so today we're going to get into chapter 3, kinematics of particles. And of course we're going to study another type of motion, and we call that plane curvilinear motion. And this time our analysis is going to be in two, axes. That means the xy coordinates. We know that motion is just, something, motion simply means that an object, it can be a particle or it can be a rigid body, is moving. Of course, in this chapter 3, section 1, we're gonna look into plane curvilinear motion. What does it mean? It's just telling you plane is, in this analysis, we're gonna study the motion in a 2D plane. So meaning we're not dealing with motion in our normal three-dimensional space, but we're gonna deal it in this analysis in two-dimensional space. So curvilinear, this word is another dynamic word, mechanic word. So it means it's along a curve. You see this little path right here, which is not a straight line, but this is a curved, this is a curved route or curved path, It isn't a straight line, so you can obviously, you can see this is very obvious, obviously curved, not a straight line. If you can determine what's the straight line and what's the curve, you can be able to determine different types of motion, because the type of motion depends on the curve the object takes, So anyway, so let's break it down, here. So we have, when you think about the plane curvilinear motion, you know that it is happening in two-dimensional space. And we call that 2 degrees of freedom. It means that your object, here, it can be particle, it can be rigid body, and that is going to move in a plane, And of course, if you think about the position, you are basically analyzing the position in two coordinates axis. If you think about in analysis like we always do. So the very first chapter 2, we study it in one coordinate axis. Now we're going to bring another axis. So you have x and then you have y axis, and we're going to study the position not only in one single axis, but we're going to study the position, in two axes at the same time, Okay, so here, look at this graph very carefully. You're gonna see we are studying, this motion of this little tiny ball or object, in two different axes. This is x. Of course, this is your number line. So the position, can be defined with this number line, and we call it the x coordinate, number, which is your x is going to be right here, So when you take a look at this ball, it is also crossing, look at that, this imaginary is a dashed line. It's crossing this y-axis right here. So therefore this position can not only be determined by the x-axis, but it can also be determined by y-axis. So if you think about it, you can say, let's say if this is, let's say 6, and then this one is, let's say 4, I'm just gonna put a number. You know that this is a 6, comma, and then y is going to be the 4. Alright, so you have a 6, 4 location, So that's how we use the x and y to study the motion, in a plane. Of course, outside in the real world, you can see like, oh, that object is here, that object is there, that object is over there. But mathematically, you have to tell exactly where this object is exactly a 6 of x and y of 4 of y, at that location. GPS even more powerful, right? It's going to tell you exactly where your location is, over the world. Now we're going to represent that, define that mathematically. So we'll form a formula of the position of this ball, instead of saying, hey, this one is a 6 and 4, we're going to say where exactly that is, so we can define any x and any y. So we'll put that into an equation. So the position of this guy, we're going to make it up like r is the position of this, okay, in 2x's. And it's equal to, we're going to have an x multiplied by a factor I, and then plus you're going to have a y multiplied by a factor j, okay? This is, of course, going into the calculus. So you will just, okay, listen like how we define the position in terms of the mathematical formula, okay? So here your x and y are your coordinates, yeah? Y and then x, and the unit vectors, see this I and then the j, and that's going to tell you the direction, okay, of this bar along the x-axis and then the y-axis. Since we now have a 2x's, you're going to have a 2 direction, okay? So that's pretty easy if you know how to read it, yeah? The position of the r is defined by, okay, first magnitude of the x and direction of the x, magnitude of the y, and then the direction of the y. Okay, so there are 1, 2, 3, 4 aspects to identify the position of this ball on this coordinate axis in 2-dimensional space. Okay. Of course, curvilinear motion is very important in engineering, physics, and also in robotics, because when we train the robots, if you can't be able to tell the robot where to go, how to work, okay, if your math is wrong, your robot is going to go like crazy, yeah? And you don't want that to happen. So also in the world, if you think about, let's think about roller coaster, yeah, roller coaster, manufacturing or robotic arms, your factory warehouse, okay, robot placement, pick and place robots. They all, okay, predict the tragedy, okay, where, you know, where you're gonna go, where you're gonna put by using these equations. Yeah, so if you think about the space, the same thing, your rocket, yeah, trajectory of your rocket, trajectory of your satellite, yeah, everything we can be able to calculate and predict, yeah, where we want to send these rockets or satellite and locate them, yeah. So the position, we can be able to identify the position by using, okay, these equations. Of course, we have studied rectilinear motion, and we are studying the plane, yeah, curvilinear motion. So you have to know the difference. Again, you have to recognize the difference. Studying is not coming to school to get, you study not to get money, okay? You study because you want to, yeah, of course, money is a part of it, but it's your major goal to come to school to study is more than money. Yeah, there's a knowledge and the intelligence, the wisdom aspect of the education that people usually don't prioritize. Yeah, it's not all about money in the world. Yeah, there are many things that are more valuable than the paper and the coin money. Okay, basically they're actually in your body system, yeah, and you can acquire it by understanding, yeah, everything about us and everything about, you know, what we have so far, yeah. You can only get it by going to school to learn yes, different, okay, different subjects, yeah, of this world, because one subject is not enough. The knowledge outside in the real world isn't enough, yeah, to nurture your system, which is your brain and your, yes, emotions and everything. Okay, so rectilinear motion, it just, here is the difference, yeah. So straight line, plane, okay. Curvilinear motion is motion in a plane. A straight line looks like that, okay. A plane looks like this, okay. A plane can be identified with your 2 axes. Straight line can be identified with your 1 coordinate axis, okay. At least that much you have to know. So we talk about the plane, and we talk about, okay, we're studying the motion in, yeah, 2 coordinate axes, x and y. I'm gonna just write it down like this. Many times I already taught you. Every time you see the x's, you're gonna go y versus x, okay? If this, yeah, y versus x, you're gonna write it that way, not the other way around, yeah? So y-axis and then your x-axis. So and that is two coordinate axes, yeah? And this, we call it a particular name for this coordinate system with two axes, and we call the Cartesian, yeah, Cartesian coordinate system. So if you think about the Cartesian coordinate system, you should know that we have only two axes, x and y. X is the horizontal and y is the vertical coordinates, okay, axis. So every time you think about the Cartesian coordinate system, you should know that it is just a fixed, all right, coordinate frame. We call this, or what is a frame? This is your coordinate frame, yeah? And of course, this is the object of interest. You're studying the motion of it, position, yeah, velocity, acceleration, yeah? So if you really think about, oh, this is a coordinate frame, it's just that we have numbers on the x-axis, numbers on the y-axis, yeah? Do you remember that we use a zone in AutoCAD, right? Engineering print, yes, sheet, and we define where the feature of our part is in like zone 6, yeah, which is a B, the zones is B6. There's a feature that I want to, yeah, emphasize on this part, yeah, just like the XY, yeah, coordinate axis. It just helps us define the position, yeah, of whatever we're studying, the particle or the rigid body or object in the space, and we're going to use this two number lines, yeah, that's it, yeah, pretty easy. Of course, when they cross, we call it a point, yeah. When we write it, we say like, oh, x is this number, and then y is, okay, that number, and the ball is going to be at that location, yeah. So when you look at it, x comma y is nothing but the cross point, yeah. So it crosses like this, yeah. I'm gonna just go ahead and draw. So see that this is the point, yeah, x, y, because it is x and then it is y, and then they cross at x, y point, yeah. And let's get into the a deeper meaning of this fixed coordinate frame. What does it mean? Of course, superficially we say, oh, this is just x, y, yeah, coordinate, and we're studying the motion, yeah, in it. And then, of course, there's another mechanical word, inertia coordinate frame, yeah. What does it mean is where our analysis, concentrating in this example on this ball is in the inertia frame, meaning like we have a fixed, okay, reference or coordinate frame. It means, in other words, it doesn't accelerate, okay. It means that we're trying to observe the motion, all right, from this frame. And if you think about the Newton's laws of motion and we apply that, we're not going to need the extra corrections, meaning like we're not going to consider, like frictional forces, okay. We're trying to take it like this coordinate system is stationary, yeah, and it doesn't change over time, yeah. So that's what we call a fixed coordinate frame. It's a little bit difficult for you to get it right away. You've got to try to get it, okay. It just mechanic dynamics is a very deep, okay, subject to study. You cannot get it right away. Nobody get it right away, okay. So inertia coordinate frame, we're doing this fixed coordinate frame, and we're studying an object. And when we study the object, okay, we know that this object is not going to accelerate in this object, okay, in this coordinate system. We're going to assume, yeah, is in stationary. We're going to assume that this object, okay, doesn't change over time, yeah. So we're just focusing on that point of the motion, yeah, without caring for before and after, yeah, just right now, okay. And the aspect of motion, we are analyzing it, yeah, and that's what we call it, the fixed coordinate frame. All right, the same thing as in chapter 2, okay. We will always study from the position. So your analysis of the motion, yeah, in two coordinate axis starts, okay, begins from the position. So we're going to analyze the position. So position is, again, is your review, is going to tell us what the object is, all right? In, of course, so right now we're not studying on a straight line. We're studying, okay, in a plane, and we're gonna, yeah, look at this plane. Yeah, I box it here like a rectangle box. So that is your plane, and we are going to define that plane by using a two coordinate axis. Your coordinate axis has the number on it. By using these number, we can be able to identify the point, okay, where your ball is. Yeah, in this case, let's just say this is an object. Yeah, where your object is. Yeah. Of course, we do have two things going on: dimensions and the direction. Yeah. So when you look at this two dimension, you're going to see a point. So that's your first dimension, and this is your second dimension, and this ball is in two-dimensional position. Yeah. So if we go into it, we're going to have a direction, yeah, where that ball is going, and we have two different directions, and we have a combined direction. Since you have two different axes, you have two directions. Okay. Since you have the directions, all right, your position in this, okay, fixed frame is going to be a vector. You have that direction and you have this direction, and you have a resultant combined direction of that ball, okay, or of that object. So it is a, the position is a vector. It's going to show you where the particle is. And our study plane is going to be right here, which is located in this plane, and we draw it. Yeah. The same thing, your origin is here, 0, 0, 0, 0, x is 0 here, y is 0 here. Therefore, the point, okay, in this example is that the point right there, yeah, identify with a little dot right here, yeah, and thus your origin is 0, 0 point, and that is again your reference point. Reference points are essential is because we use it to measure the distance from it, okay. So if you think about this example, we have a story here, yeah. So you have a person. This object is now, we define it as a person, and then this, okay, plane is your room, okay, and then here is the door, and then we're measuring the distance of this person from that door, okay. Where is this person located from this door? Yeah. So in this diagram, your person is located 5 feet. That is your x number. And then y, okay, is 3 feet. Yeah. So therefore the point is 5, 3. Yeah. So you're gonna write it like the person is standing or locating 5, 3 point on this fixed frame coordinate system plane. Okay. So from the door along the x-axis 5, from the door along the y-axis 3. Okay, so you take 5 is the axis, okay, and then you're gonna go up the axis, and you're gonna get this person. Yeah, got it. So if I have to draw, I'm gonna draw it this way. Yeah, that's your x, and then you're gonna go up, and that's your y. This y is the exact same, okay, as the one that we would draw, because when you look at it, see, this is another geometry. Okay, we use again in mechanical engineering technology, we use geometry. Okay, so when you look at it, this is a rectangle, so therefore this side and that side equal to each other, meaning like if this is 5, that's 5, if that's 3, this is 3. Okay, so therefore y is 3, x is 5, and your direction is going to go this way because it is going to this direction on the x, and it is going to that direction, which is the same as this guy, on the y. See, so your resultant direction is like that because you went straight on x-axis and you went up, all right, on the y-axis. Okay, so understanding the position is the first step to analyze your plane curvilinear motion. Okay. Okay, now we will go into the mathematics, yeah, aspect of plane curvilinear motion. Okay, all right. So when you look at it now, we're going to use equation to, all right, define the position of this object. Yeah. So I said that we're going to define the position and we're going to call it R. Yeah? See this little bold symbol. So that's your R. And R is equal to, yes, meaning the position of whatever object that you're interested to study in this coordinate system, yeah, that object is at X. Yeah, meaning like it is right here. Yeah, at X, going to the X, okay, this direction, I direction, meaning like let's say just go straight. If that's a positive, it means like we're going that way. Yeah, of course if you go opposite, that's going to be negative, so that's a positive. Yeah, and if you go the opposite direction of Y, it would be negative down here. Yeah, so meaning I'm going to the positive I direction, meaning I am going that X amount I direction. Then add meaning like I will continue to go. Yeah, I'm gonna continue to go in Y direction, which is J. Okay, going up like that. Y direction. See, it's showing you I'm going up Y direction second. Yeah, this is always first. X is always first, followed by Y. So first I go X that amount. Let's say I went like 5X. Okay, and then I'm gonna continue. Yeah. To work another, let's just say this is 3 because it looks a little short. Yeah, okay, 3 magnitude, okay, whatever unit is 3 unit up. Yeah, in the up mean like going to the J direction. Yeah, this mean up and this mean to the right. You can also write like X right plus Y, okay, up. It doesn't matter what. This is just a variable, so you can make up any kind of letters that you want. Right now, we just make it like R equal to going X that much, going in this direction. You have only 2 direction on the X, yeah, axis, that is this going that direction and going that direction. If you call going this way is a plus I, you're going that way negative I. Yeah, then we're gonna go up Y, that amount Y, okay, amount is 3 unit, and I'm gonna go up, meaning like I'm going up J direction. Yeah, J direction, which is plus J direction. So if you go this way, you're gonna be writing like minus, okay, this supposed to be a little dot, so minus J direction. Okay, got it? If you go to this direction, it's going to be minus I direction. If you go to this direction, it's going to be plus, okay, I direction. Plus is silent. Yeah, we don't really write the plus. It's automatically understood. And then of course, if you go up, that is your plus J direction. Okay, got it? Yeah, so that's what we're writing here. Yeah, the first one is my position is I went X amount in I, meaning like going to the plus, right, to the right direction of your X, yeah, on the X coordinate axis. Yeah, I went about Y amount in J direction, meaning going up. Yeah, and then of course we're gonna calculate the absolute, okay, value of that. We can be able to get, okay, absolute value of R. Yeah, so what are we doing here is we are calculating this geometry. See this? Yeah, see that is a triangle. Yeah, so if you look at it, you're gonna get like this. We know the amount from here to here, that is X. We know the amount from here to here, that is Y. Amount meaning your value. Okay, in order for us to get this, yeah, we call that is R because your position is right there. Yeah, so if you want to get the magnitude, yeah, or distance of that Y, we can be able to get it by using the, yeah, this formula, which is square root of a squared, okay, plus y squared, and that is a distance from the origin from here to here. Yeah, so that's your distance. Magnitude, of course, a distance from the origin. You can be able to get the distance from 0 to here without going from here to here. Yeah, so why? Because our geometry that we're dealing with to study this distance is a triangle. Yeah, so when you look at the triangle, you now get 3 angles, and our angle of interest is right here, theta. Yeah, so we identify the angle, and that angle is from x-axis that amount. See, it's gonna go 0 all the way to there and stop. Okay, So if you want to know the angle, this theta, yeah, we call it that's a theta angle. You're going to use this formula to get that value, okay? Meaning like what is a degree? We just take the tangent, yeah? So tangent, and then this is -1 mean power, yeah? When you look at this tangent, you can write it this way, yeah? These are all your mathematics, by the way. So theta equal to, if you see -1 tangent, it means like this, okay? So you have a tan, and then you have a y by x, yeah? Y by x. So 1 divided by tangent y by x is equal to tangent -1 y by x. Okay, this is power, by the way. Yeah, it is the same as writing like 2 to the power, let's say -1, is equal to 1 divided by 2. Yeah, we're writing that way. But of course, when you calculate, you can calculate this way. So anyway, that will give you the direction, meaning like, you know, the direction of this object, yeah, is this angle away, yeah, this angle away from the origin, yeah, from the x-axis again. If you want to say it with the y-axis, you're going to say that angle away from the origin, yeah, from the y-axis. Because you have two angles right now, and you have two triangles. Yeah, we get deeper and deeper into the math. So anyways, that's the location, yeah, magnitude is this, angle is that, and of course this is a combination showing you in terms of x and y, and in terms of x direction and y direction, yeah, defining the accurate location of R, your object. Of course, we can also get the magnitude, yeah, when you look at it, this is your Cartesian, yeah, coordinate. You also have a polar because we're putting, see, the angle right into it. So you can convert Cartesian and polar coordinate in this way. So if you have an x, yeah, you can convert the x magnitude or value of x, okay, in terms of polar. We call it polar every time you deal with this angle, yeah. We call it Cartesian every time you define the location by using only x and y. If you use the angle, we're gonna say like we are defining the location with polar coordinates, yeah. So if you think about the conversion between the Cartesian and polar, you're gonna use this two formula. So now I can, yeah, get x coordinate, x magnitude or value of x by using the angle, and that is, yeah, absolute value of r, which you can get it with this equation, and then cosine theta, absolute value of r, and you can use this equation and sine theta, yeah. So anyway, so this is how we calculate the math. Of course, you only, in this class, you know, you only need to know how we calculate. I'm not going to ask you to calculate. You know, if you do calculate, I encourage you to use MATLAB, yeah, MATLAB or Python, and program it like I show you in the last chapter. So that way you can be able to easily calculate it. Alright, so the next thing that you need to know about the displacement, yeah, and total distance traveled, just like we studied with the one coordinate axis. You know, right now we have another extra coordinate axis, but we're going to analyze. The first one is the displacement, the second one is the total distance traveled. To review displacement and total distance traveled, this one depends on the path, yeah, that one doesn't. So if you think about your displacement, you know that we deal only with the starting point and the ending point, yeah? So we're going to start with a straight line vector from the initial to the final position. So here in this example, your initial is here, and then your final is going to be here. Every time we deal with displacement, we're dealing only this, see? Okay, displacement is always identified by delta, this little triangle right there. So see the change in position. I started here, I ended here. My change in position is delta r. Yeah, see that? And don't forget, you have a define r is here and define final position is there. Yeah, so you have all of this. Sorry, all of this is two of them here, one here and second one here. Yeah. Okay. Alright, and if you think about the total displacement, again, see, S total depends on the path. You can go this way, or you can go the wiggly way, or you can go like pass it and then come back. Yeah, you can go again and again circulating and then end here. Yeah. So anyway, so your total distance traveled is always equal to, and that's a minimum, yeah, distance straight line, and greater than your displacement. Okay, so don't forget these fundamental aspect of displacement and total distance traveled in mechanics or dynamics. Yeah, so the displacement is a vector. It has a direction. Yeah, distance is a scalar. We're dealing only about the magnitude. Okay, displacement, I'm going from here to here in that direction. Yeah, and we deal only with a change. Total distance travel, we deal with the path. How did I go? Did I go ding 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 that way, or did I go straight line, or did I go curved line? Here in this example is a curved line, so therefore the total distance travel value is always equal to or greater than delta r. Yeah, so if I have to write that down, I'm just going to say like this is S total. Yeah, if I write like this, then you understand a little better. Greater than delta r. Yeah, so make sure you understand the difference. Again, you gotta recognize the difference, yeah, between what you're doing. So you're studying the location, yeah, and now we're dealing with the two location, starting location, ending location. The terms that we use: starting location, we use the location symbol R, starting initial, ending symbol R, so that means location, final location. We read it final location, initial location, okay? And this little triangle is, these are all shorthand, yeah, symbols. This little triangle is the change in the position, okay? S total means the total distance. S is the distance traveled, and that is going to be greater than or equal to delta R. Do not confuse with your symbol in plane curvilinear motion with the symbols in single coordinate straight line, okay, rectilinear motion. Yeah, they're similar, but in some in some circumstances it's different. Yeah, and our job as a scientist, engineer, technologist, you have to recognize these differences, even if they're very tiny. Yeah, the more you can recognize, your skill is better. Yeah, so people who can see can make the decision, a better decision, and they're wiser and more intelligent. Yeah, and more competent, of course, if you think about the competency. Yeah, all right. Change in, yes, a position is equal to final position minus initial position. Yeah. Now we're getting into velocity. Yeah. So velocity, we have it is a vector because we consider the direction, of the object in motion. Graphical, every time you study, or analyze the motion of interest, we draw the diagram. In the diagram is always, you always have a path, the path of the motion, and if we want to identify the velocity in the diagram, we usually use the arrow, okay, and we usually use tangent, okay, to that path. Tangent meaning like this, tangent of this arrow, we draw like that to describe the velocity of the object on that path. So every time you see this little arrow tangent to the path, pay attention. Tangent to the path, it means that we are defining the velocity of that object in that motion on that path. Okay? Now we're going to put it into the mathematical formula to identify the velocity of this example here. It's going to be variable v for velocity equal to, again, that's the magnitude. Magnitude, we're dealing with, again, the same thing, the same plane with the same two coordinate axes. So magnitude, okay, going on the x-axis, magnitude going on the y-axis. direction on the x-axis and the direction on the y-axis. Yeah, instead of trying to remember vxi plus vyj, you want to see it like I'm going that value or that distance with this direction, and I went that value this distance another directions. Yeah, so therefore your resultant direction is going to be all right, deduced or calculated from these two sub directions. Yeah, because you did two different directions when you are floating in the 2D space. Okay, all right, so anyway, so this is your running path, and that is the runner, the object of interest, and this is another runner, the object of another, another object of our interest on this path. Yeah, and they're going with this velocity, and that velocity can be identified by using this. We can get the like the accurate value of that velocity of each runner by calculating this. Even though we say VV is the same symbol, but of course the velocity of this runner could be different from that runner. Yeah, because your V on the X is different. Your I, your direction of that is also different going this way. See, your direction of this runner is that way. Yeah, so when you put the all together and calculate it, they may have the same velocity and they may have a different velocity. Yeah, so we go into the reasoning analysis. So analysis is there's not one way. We use a symbol, meaning like this can be anything. This can be any distance on that path. Okay, so how powerful the equation is. Yeah, very, very compact, and yes, we can identify every aspect of it. Yeah, the distance, the direction, the distance, the direction. Yeah. This is just a little example 3.1-1. It's just asking you to draw a velocity vector for each position of the particle in the following figure. So now you have, look at this, it's a curved line, so you also have a y-axis and x-axis, so you can identify you're dealing with a plane curvilinear motion. Yeah, it's okay. So that's the first thing, the type of motion you will identify right away. So you will come up with the right equation to solve the problem. Yeah, and then of course we have a distance. Yeah, and then we have the path curve is right there, and we have to draw the vector, and we already knew the vector is the tangent to the curve. Yeah, so all we have to do is to draw the velocity arrow, arrow line, with the arrowhead pointing to the direction of this object right here. Now we drew. Okay, so we have drawn. The very first one is a tangent to the first curve. The second one is a tangent to the second curve. So if you look at it, that is the curve. If you look at it, this is the curve. Curve means like that. Yeah. So it has a kind of like a I would say like it always have a center, where you can be able to measure the radius. Yeah, so we call it curve, meaning broken circle. Yeah, this is a circle, and you can cut your circle in many different ways to make many different curves. Yeah, we have an irregular curve like that. We have profile curve like that. Yeah, we have a perfect circle curve like that. So right now it's a profile curve right here. All you have to do is just draw the tangent. Tangent means every time you draw a tangent, it means that you're drawing a line, connected to the curve at a point. Yeah, see that? So that's what we call tangent. Yeah. So these are your mathematics. Okay. So if you draw like that, you're gonna get. Of course, my drawing is not perfect, so this is a perfect drawing. See? So that's the tangent line. So you're gonna draw a velocity vector, for each of this position. So this is your velocity. It is denoted by arrow with a head pointing, meaning like, hey, this velocity, not only it has magnitude, but it also has the direction. The next thing that you need to know is the difference again between the velocity and speed. Of course, this is our common word that we use in the real world. Nobody use velocity, right? They always say my speed is. Yeah, velocity is just a speed, Okay, and speed has just magnitude. If you think about speed, it only has the value. If you think about velocity, it has a value and it has a direction. Yeah, and that is a common word that we use outside for velocity and speed. And this is that we use for velocity in mechanics. Yeah, and we also use speed. Speed is not equal to velocity in mechanics. Okay, of course, outside world, when you say speed, you meant velocity as well. Yeah, but of course you usually don't you usually, like, you don't include the direction, at all. Yeah, you just ignore it and you just talk about speed, like 60 miles per hour, so and so. Yeah, but in velocity and speed, when we do calculation, this matters, yeah, a lot. Of course, when you're driving, your car actually is showing you, yeah, which direction you're going in your dashboard or on the rear mirror. Yeah, it's going to show you you're pointing north or you're pointing northeast. Yeah, and you're pointing south, so and so. Yeah, so there is the direction and your car is showing you. It's just you're ignoring it. Yeah. Another small conceptual problem here in this chapter. So here you have a situation. You're gonna determine, okay, whether the speed or velocity is changing. Yeah, you're gonna determine if speed or velocity is changing in this situation. Your problem is defining right here. You're gonna say either both are changing or neither is changing. Yeah, so now we're dealing with constant, yeah, speed. So when you look at it, it's set a car cruise control, meaning it's going with the same speed. Yeah, it's set to a constant. It's set it so here constant. Yeah, 50 miles per hour. Yes. So if you have a constant speed, 50 miles per hour, yeah, and your car is driving on a example like this, on a level, straight away, then you understand there is no change. Yeah, so therefore neither change. There's no change in your speed because you're going with 50 miles per hour. 50 miles per hour here, 50 miles per hour here, and 50 miles per hour here. It's set so in the problem going with the 50, constant speed. So therefore neither change. The next one is a car cruise control is set to a constant 50 miles per hour, and then the car rounds a curve. Yeah, see, it is going straight line, and then it starts to turn. Yeah, rounds the curve mean like you're driving on a curve from the straight line. Yeah, so you have straight here, and then you have curve here, and then you drive. Yeah, so there is a change in the path shape. Yeah. So here your car is going a constant 50 miles per hour, yeah, and then you turn. So when you turn, your velocity will definitely change. Yeah, you can't go with 50 miles per hour, so your velocity will be definitely less than 50 miles per hour. Okay, because you have to slow down to make that curve. Otherwise, you're gonna, your car will come off of the road. Yeah. Next one is your car is going on a cruise control. It was set constant 50 miles per hour and then your path change. Then now your car is going over a hill. Yeah, see this, there is a hill. So every time you have a path change, okay, your velocity changes. Yeah, so therefore if you go up over the hill, you definitely need to, increase the velocity. You would do, yeah, and then you're gonna go up another hill like that. Yeah, um, there is, like, I think some, like road signs. Maybe let's say like you have like a road sign here. Yeah, you're going up the hill, but the road sign says please reduce to like 30 miles per hour. You're driving 60. Yeah, it won't work. Yeah, you're gonna feel like, why do I have to slow down? And you feel bad because normally every time we climb a hill or whatever hill that is, we speed up. We tend to speed up. Yeah, if you go with 20, then you want to go with a little more than 20. Yeah, to make that hill. So anyway, velocity will definitely change. Then your car has a cruise control. You set it to 50 miles per hour and you're driving. And you're going to go up a hill. Yeah. But then this hill has a constant grade. You got to go up the hill. So another change in path. But in order to make the hill, okay, since it is like driving up a hill, but it has a constant grade, okay, if you reduce or if you reduce or increase the speed, it's not going to make it. Yeah, normally you're gonna have to keep the constant 50 miles per hour to comfortably make again the constant graded hill. Okay, the constant graded hill is not like this. It's just going, like straight up like that. Okay, so in order for you to make it straight up, you have to either, if you keep the fixed constant velocity, it's gonna make it easier for you to overcome that hill. Yeah, so therefore velocity is not changing. Okay, and another daily scenario, if you drive the car and you're going with a constant speed 50 miles per hour, and then you're going to apply the brake. Okay, and of course you are on a straight. Okay, now see there's no path change, you're definitely on a straight line, and then you're going with 50, and then you're going to go ahead and then applies the brake. Okay, at that time your velocity is both, it doesn't change because you still have the 50 miles per hour, because it is abrupt braking. So you still have a 50 miles per hour, and also your velocity might change. Okay, so this is a trickier situation, but then we usually try to identify by whether you are on a straight path or a change path. So right now you're still on a straight path, so therefore both. It means like it won't change neither, it will change. Okay, which is a change, N for not change, and C is for change. If it's not change, you're still at 50 at that point of when you apply the brakes on the straightaway. Now we're going to put this three different types of velocity, and you have already studied them on a straight line. Now we are in a two coordinate axis, 2D plane. So now velocity, regular velocity, you have a magnitude, direction of x, you have a magnitude and direction of y. And you can be able to get the combined velocity. Then average velocity, the same thing, your v, AVE, is going to be the change in position over the change in time. Don't forget this little change right there. Instantaneous velocity is going to be the little change in r and the little change in t. So little change in position and little change in t, because we are concentrating, okay, at a point. Okay, this is more average. This is just a regular velocity, and this is a point, so therefore your change is very, very tiny. Differentiation, and of course that's just a regular change. Try to review this from your chapter 2. This is just giving you a little yellow comment, to get your attention. This instantaneous velocity is taking mathematically is the derivative, which is operation is differentiation. Derivative of a vector, the same as taking the derivative of a scalar. So we understand the velocity, we're dealing with the magnitude and direction. And of course you gotta understand whether the derivative, if you operate derivative of a vector, meaning like taking the vector, taking differentiation on a vector, you gotta understand if that is the same as taking the differentiation of a scalar without the direction. So these are little tiny things. So we're gonna take a look at that with the examples. So here you can see the differentiation. This is just symbol. Don't try to feel bad about it, because we're just breaking down into different parts, because now you have two different parts. And we have two different, of course, direction. And you also have a resultant, the combined, which is your combined position, and then the combined direction. Okay, so this is a combined position and a combined direction. So you're dealing with three different things, at the same time. So when you do the differentiation, even though we say like the instantaneous velocity is dr divided by dt, when you define this r, you gotta put in all of its subcomponents of r. So the subcomponents is r, x direction is I, r, y direction is j. Of course, we're going to start introducing the real world, the third dimension, which is your z-axis, your magnitude in z-axis, and the direction of that z-axis. Okay, and you're going to differentiate each component and add them up in order for you to get the differentiation of your velocity. Okay, and then of course we can take each part out because it is a mathematical formula, so you can be able to do your algebra meaning like we are moving we are moving the mathematical components on the right side of the equation to the left side of the equation. We can put the component on the left side of the equation to the right side of the equation without disturbing the equality of the two sides in the mathematical formula. So if you do that, let's just take this out to the left side, and we're gonna bring this to the right side. So that's what we're doing right here. So all you do is you're gonna take it to the other side of that. So you're gonna have r x I which is equal to just trying to differentiate separately. Okay. All right. So now without doing algebra on the first equation. Okay, this is just showing you the calculus part of your differentiation. So if you want to differentiate or solve this value, what you do is first you are going to differentiate the first value, and then you're going to differentiate the direction. So this is your magnitude. So we're going to differentiate the magnitude, and then we're going to differentiate the direction, because I is the direction and Rx is the Rx component of the location. So magnitude. So we are differentiating the magnitude, leave your direction alone, and then leave the magnitude, and then differentiate the direction. Okay, see that we did the two differentiations, and then of course add them up because they're the same anyway. So you will get the combined differentiated values at the end of it. So you have drx and then divided by dt and then I. This just showing you the little symbol. Don't worry about it. You don't really have to know it, but understand that this is how we solve the calculus operation, which is called a differentiation. So y is di by dt equal to 0, which is this guy. Di by dt is 0, meaning we are differentiating the direction. Okay. So that's because remember where we are studying. So the plane curvilinear motion we usually study in a fixed coordinate system, and this is the reason why the vector we call, of course, without putting the value into it, because we're not in a specific problem here. We're just studying with a unit vector. When we call it as a unit vector, meaning like there's no specific magnitude of that vector, and we call it just one unit vector. So a unit vector in a fixed coordinate system, it doesn't really change over time. Meaning like it doesn't move, and then the magnitude of that unit vector doesn't change, and that's the reason why when you differentiate the I part, which is the direction part, you will get 0. So that's what is talking about. So velocity, when we do the differentiation, we're just looking at it with time. So that's a time derivative of your position is your velocity. Velocity means we are looking at the location, which is your position against the time. Meaning studying, again, your time is, even though we use it time, we're just looking at that behavior, the motion behavior from one point to another. And there we have that amount of time interval. And we identify this action or this behavior or this instance activity in this way. Okay. It's about knowing like your symbols, what is it about in real real like what's going on. So when you read the mathematics, don't just read the character, you understand what it really means outside in the real world. Okay, for me, I'm looking at, when I see this, I know that I'm dealing with something, okay, at a position, and I have an amount of time, okay, which is from here to here, that I'm studying about this guy. That's what I get. Okay. um of course, in the unit vector, when we write this, I said I'm going to explain what this little thing, it means that we are looking at a vector, but this vector doesn't have many different values. It only has unit 1. Yeah, so it means that we're dealing with a unit vector in a fixed the Cartesian system, because we're identifying with the xy. There is no angle. Yeah, if you have an angle theta, of course, you will go into the polar, yeah, coordinate system. Right now we're dealing with the Cartesian, yeah, coordinate system. And of course, you can be able to calculate, yeah, your velocity by using the subcomponents of that velocity identified by your xy. For plane, it's going to be 2 axes, and for 3D, yeah, 3-dimensional, it's going to be 3 axes. Yeah, that's all it said. And it said, please pay attention every time we deal with the unit vector, yeah, on the xy coordinate system. Since we're dealing with a fixed coordinate system, your unit vector doesn't change over time that much, so therefore it is 0. Yeah. All right, then we will go into a little bit about this vector. So when we do the differentiation or taking the derivatives, you know, of a vector, and of course we're dealing with the Cartesian. Every time you see Cartesian, your brain got to have like xy here in xy coordinates, right? And of course you can get that derivative of a vector. Operation again, mathematical operation is in calculus, differentiation, and we're gonna do differentiation is nothing but just, you know, like we're differentiating, trying to get the value by studying individual components, yeah, to get the resultant. Because your vector, if you break it down into different coordinates, yeah, what you want to get is a resultant. Yeah, so your velocity here, your vector, yeah, and you see the distinct component x and components y, and each one of them has a magnitude, yeah, and a direction. Yeah, it has only 2 directions, going this way or that way for x, yeah, and going this way or that way for y. Yeah, so your direction, r and j, magnitude given to you by the position, because it is a position number. Yeah, and of course, if you get the velocity, you can be able to get the acceleration, so forward direction. So if you want velocity, you can differentiate position. If you differentiate velocity, you're going to get acceleration. And that's what we're talking about here. And don't forget our dot, yeah? So little dot with the position will give you velocity. Little dot with the velocity is going to give you a, yeah? It's just a way of writing it. Of course, I'm going really fast because everything is in my head, but for you, you gotta go slow to take in these things. You know, you won't get it right away. By the way, 1 semester is too short to get it. Yeah, I totally understand if you get a little bit about it, okay, but and don't just stop it. Yeah, you will have to continue to study if you are serious about the career in our line. Yeah, everybody wants to become engineers and like that, but they don't want to do the work. Yeah, so in order to increase the competency, you have to actually study. Yeah, and studying takes time. Okay, everything takes time because you're training the physical thing inside of your brain, which is memory. Yeah, memory unit. They're not something that is they're just so tiny particles, yeah, but then you can train it. Yeah, you can train it to package and remember, just like your computer chips. Anyway, I try to really get into that, please. Yeah, don't just stay on the one level of life. You understand? You should be able to understand it by now. Yeah, I've been telling it to you every lecture that I have. So anyway, so you have position vector and acceleration. Want to get the velocity, differentiate r. Want to get the acceleration, differentiate v in Cartesian coordinates. Yeah. All right. And then we'll get into a little problem right here. A fisherman sits in a motorboat. So in your brain, you are drawing like that, okay? So fisherman in a motorboat, yeah? At the shore of a river, whatever, flowing downstream. All we need is going down, yeah, downstream. And of course, the velocity is 4, yeah, meter per second. So anyway, so these are the things you gotta sketch, yeah, in your brain. If you cannot sketch it in your brain, sketch it on a paper like this, yeah. And then the fisherman wishes to reach the other side of the river, yeah. So you're on one side, and you're gonna want to go to the other side of the river, yeah. So if the river is 60 meters wide, now talking about it. So river has a two side, this side and that side. Yeah, your river is flowing with the 4 meter per second. Yeah, the fisherman is sitting in the boat. Yeah, it's on one side and he wants to go the other side. Yeah, so if that river is 60 meters wide, now I'm telling you the dimension of the river. Yeah, in the motorboat, this guy, yeah, is the maximum speed. This boat speed is a 3. Yeah, river flowing 4. The speed of the boat is 3, and that's the maximum. Yeah, 3 and under. Respect to, of course, every motion is respect to motion of the other. So we are neglecting all other motion in the environment and concentrating motion of the boat against the motion of the little river right down there. Yeah. And of course, the river has a side. Yeah. So these are the information first you have to put into your brain. Yeah. So what is the shortest amount of the time it could take the fisherman to perform the crossing? Yeah. So he want to go that way, and we want to find the shortest amount of time. Yeah. So it also says, please note that the flow of the river is parallel. It's a parallel to the shore. So the flow is going this way, and you have a shore number 1 and the shore on the other side. They are parallel. Yeah. Of course, now we draw it, yeah, systematically instead of this a brain sketch right there. So anyway, but that's what it is. Yeah, everything here 60. River flow rate 4, boat flow rate 3. Fisherman on a sitting boat. Okay, want to go from here to there. Yeah, so if you want to go from here to there, first you go there. Yeah, and then you're gonna since the river is flowing this way, so this is your boat, and then that is the river. The resultant is going to be that way. Okay, so we have 3, 4. So therefore, you use the Pythagorean theorem, and you're gonna get the 5. Do you remember? Yeah, you're gonna do this thing. Yeah, x squared, and then y squared. Yeah, Pythagorean theorem, which I already showed you. So put that in, and you're gonna get this. Yeah, 5, 4. The resultant magnitude, direction. The first direction I, the second direction j, resultant direction. Okay, I plus j. All right. So now we have everything. All the information is given to you, and this is written information. That is a drawn information. Yeah, diagram is better because your brain likes the diagram more than the text. Yeah, so if you read this, you don't remember. You have to repeat 1,000 times to get it in the brain. If you draw a diagram, all right, your brain can absorb that faster than this. Okay, so therefore, please, in science, we teach the students to draw the diagram. Okay, everything is a diagram. So please make sure that you draw that. So now we gotta find the time to perform the crossing. It shows you down, down, down from here to there for the choices given to you here. Yeah, we have 20 seconds, 15 seconds, 60 by 5 seconds, and then we have a 60 by 7 seconds altogether. And your test is to choose the best option. Alright, so in order for us to get the time, you're going to have to calculate the time, yeah? So the time is the river distance, because your initial point is here, the final point is right there, yeah? So that's your distance, the shortest distance is set as so therefore you're going to take distance from here to here divided by the speed, okay, which is your velocity. Since you are going with the boat, you have to use the boat speed instead of the river, yeah, because you're going that direction. You're not going this direction along the river, yeah, you're crossing the river. So therefore from here to here is your distance, and divided by the speed of the boat is meter per second, yeah. So unit meter cancel, your second is, yeah, under the first divider, yeah, then second divider under it, so you're going to put it up and you're going to get the second, yeah. So time is 20. 60 divided by 3 is 20 seconds. Okay, because remember, yeah, your velocity, yeah, is equal to change in position, yeah, divided by time. The change in position is this, yeah, your velocity is this. So therefore we can calculate the time interval that we're studying this motion. Yeah, it happened in 20 seconds. Yeah, the boat can get from there to here, overcoming this river speed. Okay.